Hi, my name is Julian. I'm presenting a retrospective on our paper, Learning a Structured Neural Network Policy for a Hopping Task. Our paper was published with my co-authors Jules Kosolinski, Alexander Herzog, and Ludovic Righetti as a RAL journal paper with proceedings in IROS in 2018. The paper contributes a way to learn the dynamics of the system, how to optimize a hopping policy, and two different ways to transfer the optimized policy to a neural network policy. One of the network's policies learns the feedback and feed-forward gains. This allows to inspect the behavior of the policy by analyzing the outputs. In the following, I will talk about the technical as well as the research lessons learned and things I would do differently from today's standpoint. Let's start with technical lessons learned. We found it important to have a short experiment round-trip time. For instance, initially we trained large neural networks taking over 1 day to train. We switched to smaller networks and brought the time to rerun all our experiments in the range of 5 minutes. This allowed us to try new research ideas quickly. One important step of achieving this was by automating our experiments, such that we could run experiments with a single command in parallel. For this, we used a Python script to generate a makefile and then run make to execute our tasks in parallel. Initially, we trained our networks on GPUs. We found that for our control policies, we were able to leverage relatively small networks with 3 hidden layers and 10 neurons. We found that these small networks train fast on CPUs at similar speed as on GPUs. This allowed us to switch from GPU to CPU training and to utilize parallelization over multiple CPU cores. Last but not least, we ran our experiments on a cluster. This came with the overhead of porting the code to run on the cluster, debugging errors on the cluster, as well as sharing resources with other users. In the end, we found it easier and faster to run the experiments locally on a workstation with many CPUs. Next, I will talk about research lessons learned. Initially, we missed to rule out experimental bias for the real robot hardware experiments. In particular, we changed the angle of attack for the hopping robot manually. In the end, we removed this bias by automating the floor movement. This made the experiments more reproducible and changed the findings in our paper. We didn't manage to learn the dynamics directly on the real robot hardware due to unmodeled disturbances. Most likely, the disturbances come from the cocking torque of the motors. In the end, we used only simulated data to train the simulation and real-world policies. Using proximal policy optimization, we were not able to train a feedback policy. We hypothesized this is due to the instability of learning the desired state and feedback matrix at the same time. This has been explored further in the meantime by other authors. Last but not least, a few points that I would do differently from today's perspective. At the beginning of our research project, we were not sure about which network architecture to choose. Therefore, we spent significant time training different neural network architectures. To save time, we should have converged on an architecture earlier. We used different robot properties in simulation versus on the real robot for historical reasons. We kept using different robot properties to demonstrate the robustness of the trained policy to different robot platforms. From today's standpoint, I think we should have updated the simulated properties to make the simulated and the real robot experiments more comparable. This is also as the transfer to different robot platforms was not the main focus of our publication. For our task, we choose a metric that helped to see the optimization progress. The metric that we used was the mean of the positive hip velocity squared. However, naturally a jump is better the higher the robot manages to jump. Therefore, I would use the metric like the maximum mean jump height instead today. In our work, we used the hard impact contact model without foot slippage. We chose this model to simulate hard impacts properly. However, slippage was important when we were testing the robustness of the controller by perturbing the floor slope. Therefore, we should have used the contact model allowing slippage. For instance, we should have chosen a well-tuned spring-damped contact model. Thank you for listening.